So by this point, we've done a pretty good exploration of a lot of the forces we deal with on a day-to-day basis. The gravitational force, weight, the normal force, friction force, tension force, even the weird situation of the spring force. But all of the situations we've looked at so far have been on flat surfaces. But what if our object is located on a tilted surface? And that's what we're going to look at today, forces on inclined surfaces. So let's start with a pretty simple scenario. You're pushing a box up a ramp at constant velocity. Now, a couple things here. We would say this is the angle of the ramp theta, so that could be 30 degrees above the horizontal, 40 degrees, I don't know. That's not really that important now, but we just want to make sure we know what that is. So we're pushing it up a ramp at constant velocity. Now, since it's at constant velocity, we know the forces must be balanced, but let's go ahead and start off by making a system schema. Well, first off, we know the box must have a gravitational force with the Earth. Pretty straightforward. Additionally, we know that the ramp is what's actually pushing up on it. It's not on the Earth, it's on this ramp. And it's important to separate these in this context. So the box has a normal force and a friction force for the ramp, and between the Earth and the ramp there is a gravitational force and a normal force. And in fact, there's probably even a friction force there too. But lastly, we have you, and you are pushing the box. We could call that normal force, but let's go ahead and call it a push force. And you have gravity with the Earth, you have a normal force of the ramp, and you have a friction force of the ramp. And let's go ahead and say that we are looking at this box here. So we have 1, 2, 3, 4 forces on the box. Fg, Fpush, Ff, and Fn. With those 4 forces, let's create a free body diagram of the box. Now first, we draw the box as a dot. Nice and simple. And let's go through these one at a time and make sure we have all the details correct. So first off, we know that gravity must be going straight down. Gravity always goes towards the center of the Earth, so it's not going to go downward on the ramp. It's going to go straight down to the center of the Earth. Now, one quick thing, I'm drawing them here just to let us visualize them a little better, but I'm going to zoom in with a more proper FBD over here on the right. Well, we also know that you are pushing it up the ramp, so parallel to the surface of this ramp. That will be F push. But friction is also parallel and opposite the direction of the slide. So since the box is going up the ramp, friction must be going down the ramp. And we need to remember that friction is always going to be parallel to whatever the surface is. Remember, it must be parallel. And additionally, we have a normal force, and usually our normal force goes straight up, but that is on a flat surface. Now that we have inclined the surface, remember normal means perpendicular, it's the perpendicular force, it must be going at 90 degrees to that surface, so the normal force is always going to be perpendicular to the surface of the ramp. So these are our 4 forces, okay? Now, it looks a little complicated, and we're not quite sure if we've drawn them all balanced or not. We'll get to that more in a second, but what's the next step we typically do is, well, we write net force equations. So let's go ahead and say we're going to draw our horizontal and our vertical axes, and I went ahead and labeled these plus y, plus x, minus x, so I know which way I'm defining positive and negative. And we go ahead and write sigma f, which, since it's moving at constant velocity, sigma fx in the horizontal direction will be 0, and sigma fy in the vertical direction will be 0. But this is where things get a little gross. Because if we look, we've got 4 forces. Unfortunately, only one of them, Fg, is on an axis. In fact, we have 3 different forces that are not on axes, and they're all related to these axes by the angle of the ramp theta, but which piece is, like for friction, where is the Fx, where's the Ffy for the push, where's the F push x, F push y for Fn? There's a lot going on. We've got 3 different forces at angles and only one on the axis, and this is pretty gross from an analysis standpoint. Is there a way we can make it much simpler? Thankfully for us, there is. So let's just go back to drawing the FPD. Fg is going down, F push up the ramp, Ff down the ramp, Fn perpendicular to the ramp. Alright, let's go ahead and once again draw our axes, our horizontal and vertical axes. And what I want to notice is that only one of them is on an axis. But, looking over at the ramp scenario, you see that 2 of these forces, F push and Ff, are parallel to the ramp, and Fn is perpendicular to the ramp, so there is a 90-degree angle here, like there, and a 90-degree angle there and there. So why don't I just reframe my axes? In fact, what I'm going to do is I'm going to take every axis here and I'm going to rotate the whole thing by theta. So I'm going to rotate this piece downward by theta, to the right by theta, upward by theta, and this way by theta. And by doing that, if I look at, for instance, this one, well, this is theta above the horizontal, so I'm going to go at the horizontal and I'm going to go upward theta. And when we do this, we end up with this scenario here, where I now have a new set of axes. And you might be thinking, well, wait a second, how can we do that? Well, remember, motion in the horizontal and vertical dimension is independent. But what is horizontal and what is vertical? You know, that's really up to the angle our system is at, and why don't we just reframe it? Because we can define our axes as, instead of being flat and straight up and down, let's make it parallel to the ramp and perpendicular to the ramp. The independence of motion should still apply. So now I'm going to rotate my axes and have one axis parallel to the ramp. So I have plus x and minus x. And you'll notice I put the parallel symbol here just to kind of help remind myself. And additionally, I'm going to have plus y minus y, but these are going to be perpendicular to the ramp. These axes are still at 90 degrees with respect to each other. But what I have done is I have made it so that 1, 2, 3 of the forces are on the axes, and only one, Fg, is not. Okay, now when I did this, what we're actually going to do is this angle right here will be theta. And that may not be immediately clear, but remember, going back a step, we rotated every piece by theta. So originally, negative y was here, and we rotated this direction by theta. So now going from where negative y was to where it is now, this angle here will be theta. Well, now let's look at the net force equations, but we're going to recontextualize them a bit. So once again, I've got my FBD drawn here, and I've got my axes, one axis perpendicular to the ramp, which I'm going to go ahead and label plus y and minus y just to make myself consistent, and one axis parallel to the ramp, plus x and minus x. Now, it didn't have to be plus and minus this way or that way. I'm just doing that because that's usually how we see our coordinate plane drawn. Well, if this is the case, when I have sigma fx is equal to 0, well, x is really sigma f in the parallel direction. But since this is moving at constant velocity, all of the forces parallel to the surface of the ramp have to be balanced. They all have to be balanced. And if that's the case, well, what forces do I have in the parallel direction? Well, one, I have my push force, I have my friction force, but now Fg is no longer on an axis. Part of it is parallel to the surface, part is perpendicular to the surface. So I'm going to specifically look at Fg, specifically the parallel component. So I have F push plus Ff plus Fg parallel must be equal to 0 since we're at constant velocity. Well, F push and Ff are going to stay the same, but how do I know how big this Fg parallel is? Well, let's look. This is theta, and it is opposite of theta, so this would be Fg sine of theta. So I have F push plus Ff plus Fg sine of theta is equal to 0 because those are all the forces parallel to the surface of the ramp. Now, a couple things here. How exactly do we define the direction of these? Because it's no longer just left, right, up, and down. Left, right, up, and down are now a little more complicated. So typically what we would say is that F push is up the ramp and Ff and Fg sine theta are down the ramp. That's totally acceptable to write it as Ff is 10 newtons down the ramp. That's saying its magnitude and its direction. But we also know that sigma Fy is also equal to 0. So the forces in the perpendicular direction compared to the surface of the ramp must also be balanced. So we have sigma F perpendicular is equal to 0, and what are the forces in this direction? Well, definitely the normal force, because it's always perpendicular, but we also have a component of the gravitational force, specifically the perpendicular component of Fg. So Fn plus Fg perpendicular is 0, and how do I know how big this one is? Well, it is adjacent to theta, so that will be Fn plus Fg cosine of theta is equal to 0. Additionally, what would I call the directions for these? Because once again, they're not really up and down. FG is perfectly down, but we could also say that these two particular parts are perpendicular to the ramp, so you could say Fn is up perpendicular to the ramp, and FG perpendicular is down perpendicular to the ramp. So we were able to create net force equations much more simply because we only had one force at an angle rather than three. So let's go through some tips for creating FBDs and net force equations for any sort of inclined surface. Now, just to make sure we understand what I'm drawing here, I've got one over here, I've got one over there. These thetas would be different, but they're both theta. And we would have this one, we'll say, is at rest, and we'll say this one is moving upward on the ramp. Is it moving at constant velocity? I don't know. Is it accelerating? I don't know. That's not important, but we have one that's moving, one that's not. Well, the first tip we need to know is that we want to set our axes parallel and perpendicular to the incline rather than perfectly horizontal and vertical. Doing that really simplifies how we can look at all the forces here. Now, once we've done that, we can go ahead and say, well, FG is always straight down. Always down, and when we've rotated these axes, it should be the only one not on an axis. FF will always be parallel to the surface. Now, for this one over on the right, this object is at rest. So gravity is trying to pull it down. The only way these forces can be balanced is if there's a friction force, a static friction force, going up the ramp. Comparatively, I have this system over here being pushed up a ramp, and if it's being pushed up the ramp, causing it to move in that direction, well then the friction, in this case the kinetic friction force, would go down the ramp. Friction may be up the ramp, may be down the ramp, it depends on the situation, but it's always parallel to the ramp. And lastly, the normal force is always perpendicular to the ramp. It's always going at 90 degrees from that surface. Alright, the next tip is that we set theta, and this is a crucial step and where I see most people make mistakes, is once we start trying to analyze these, what angle on this picture matches theta, the incline of the ramp? It is always going to be the angle between FG and the perpendicular axis. So it is between FG and the perpendicular axis, between FG and the perpendicular axis. That is real crucial. We want to make sure we can recognize that instantly. And then lastly, we can say, well, we could find components of FG, because FG is the only one not exactly on an axis. And we could say that the parallel component will end up being FG sine theta, because it is across from theta. And FG perpendicular will be FG cosine theta, because it is adjacent to theta. The reason why this is occasionally confusing is because what we're actually seeing is that we have, if we say that the parallel direction is the x direction, it involves a sine. And if we say that the perpendicular direction is the y direction, we have a cosine. And that is switched from what we're typically doing. We have to be real careful that we know, okay, is this next to theta or across from theta? Really make sure if we should be using cosine or sine properly. So now let's look at a more complicated problem. Let's say we have a 2 kilogram box and it's sliding down a 30-degree incline. So by that we mean it is 30 degrees relative to the horizontal. And if the coefficient of kinetic friction, mu sub k, between the box and the surface is 0.3, what is the acceleration of the box down the incline? So this box is not even going to be moving at just a constant velocity. It's going to speed up as it goes down the incline. We need to figure out how exactly is this going to work. Now, the first thing you need to be able to do is you need to be able to take this situation and, one, draw an FBD that's appropriately laid out, and write some net force equations. I want you to try this step on your own. So go ahead and pause the video, and in your notes, go ahead and draw what you think the FBD should look like, and additionally what the net force equations should be, including the different components. So pause the video, give it a shot. Well, hopefully you gave it a try, but let's now start talking through how we would do this. One, we want to set our axes parallel and perpendicular to the ramp. So I'm going to go ahead and draw my FBD dot and my axes, one parallel, one perpendicular. Once again, I have plus y minus y plus x minus x. I'm just doing that to always make sure I remember which side is positive, negative. I'm just going to make it look like a normal coordinate plane. Now let's start drawing our forces. We're going to have gravity going straight down. We're going to have friction going up the ramp parallel to the surface because it is sliding down the ramp. And we're going to have a normal force going upward perpendicular to the ramp. There's nothing else required here. Because it is sliding down, you don't need anything pushing it. this should be enough. Now, I will say what is important is that we're going to go ahead and also find the components of FG perpendicular and FG parallel. And if we know it is accelerating down the ramp, well, we know in the vertical dimension, and by vertical I mean perpendicular to the ramp, Fn must balance the perpendicular component of gravity, but in the accelerating direction, Ff cannot balance the parallel component of gravity. In fact, the parallel component of gravity should be bigger. So when I write my net force equations, I will have sigma Fx, which in this situation I mean sigma F parallel, is equal to the mass times the acceleration. It's not equal to 0 here, not 0, because it is speeding up going down the ramp. And in the perpendicular direction, I have sigma Fy equals sigma F perpendicular. That one is 0 because it's not accelerating up the, upward off the surface or downward into the surface. It's only down the surface. So in the parallel direction, I'm going to have Ff, this force, and Fg parallel, that'll be this one. Those have to add together to equal the mass times the acceleration in that parallel direction. And in the Fy direction, we have Fn and Fg perpendicular, and those must add together to equal to 0. Lastly, let's take that a step further and say Ff plus Fg sine of theta, because it is across from the theta, will equal ma parallel, and Fn plus Fg cosine theta will equal to 0. So I've gone ahead and written down our givens for this particular situation, the mass being 2 kilograms, theta being 30 degrees, and the coefficient of kinetic friction being 0.3. And I went ahead and rewrote the two net force equations we found. Ff plus Fg sine theta equals the mass times the acceleration, and Fn plus Fg cosine theta equals 0. And remember, the question was, what is this acceleration? Well, to find that, we need to start figuring out some other pieces. First, well, to be able to do that, I need to know what Fg is, and I need to be able to know what Ff is. Well, to find Fg, we just multiply the mass times g, so 2 kilograms times 10 meters per second squared, multiply them together, will be 20 newtons straight downward. Okay, well, I can plug that in here, but that's not going to give me the friction force. How can I get the friction force? Well, I have the coefficient, but I also need the normal force. So I'm going to actually have to go to this other equation and solve for the normal force to be able to then go back, find the friction force, find the acceleration. So let's plug Fg into this equation. So we have the normal force is equal to, okay, now careful, I wrote minus 20 here, minus because Fn is upward, I said that was a positive direction perpendicular to the ramp, and downward perpendicular to the ramp, I said was the negative direction. So it'll be Fn minus 20 cosine of 30 degrees equals 0, and you solve for that and you get that Fn is equal to 17.3 newtons. Well, I can now use that in the coefficient to find the friction force. The friction force is the coefficient times the normal force, so 0.3 times 17.3 newtons gives me, in your calculator, a friction force of 5.19 newtons. Now we just need to go ahead and start plugging some numbers in here. We have to be real careful with our positives and negatives. If you go back and look at the picture we just drew, we said down the ramp was positive and up the ramp was negative. So friction was up the ramp because it's sliding down, so I'll be negative 5.19 newtons, plus this component of gravity was down the ramp, so it'll be plus 20 newtons sine of 30 equals mass times acceleration, 2 times A. We go ahead and start plugging numbers in. You solve for this side, you get 4.81 newtons equals 2A, and you get that A is 2.4 meters per second squared down the ramp. And we know for a fact we did it right because this came out to be a positive number, which that would be down the ramp. So we have taken only a few pieces of information, including that angle of the ramp, and I was able to find how much this object was accelerating as it moved downward. So what are the main takeaways for this lesson of forces on inclined surfaces? Well, we're really going to start piecing together everything we've learned about forces up to this point, but we're no longer going to look at flat surfaces, we're going to tilt them. And when we do that, we want to make sure we can draw free body diagrams accurately for objects on those surfaces, which means 1, Fg is always down, Ff is always parallel to that surface, and Fn is always perpendicular to that surface. And we need to make sure they are balanced or unbalanced appropriately by looking at how exactly the different pieces fit together. We need to redefine the axes. So rather than having a horizontal and a vertical axis, I'm going to rotate them and have a parallel axis and a perpendicular axis to more easily find forces at angles and write net force equations for objects on inclines. Remember, the really crucial thing here is you need to be able to know Where is theta, the angle of that incline on your FBD and with respect to those axes? And it should always be between FG, going straight down, and the perpendicular part of the axis with respect to the ramp. And then lastly, can we solve for unknowns with these problems involving inclines just by using the net force equations and any givens we're given to get to that final result?